All right, in this video I'm going to be talking to you a little bit about surface area and how we're going to compute that using a double integral. Okay, and so to start our discussion, I'm going to show you where the formula for surface area that you would see in a textbook comes from, and we're going to center our discussion around z equals f of x and y, which is going to generate a surface, and that surface could have some area. I'm interested in the amount of that surface that sits over a very small piece of area in the plane, maybe delta area. So I'm going to call this delta A. And I'm going to mention that that amount of area is given by delta x times delta y. Okay. I'm just going to throw that out there. I'll need that later. And then I've got my surface z equals f of x and y, which I think I drew pretty well there. I think that's a good one. But I'm interested in drawing the tangent plane to that surface. Okay, now it would be pretty easy for me to draw it right over here at this little maximum, but I really want this tangent plane to be tangent to the surface at the point right above here, the point closest to the origin. Basically so that I can show you the way that this plane works. Because what we're going to do is we're going to say that for very small delta areas, and I'm envisioning this being a very small piece of my overall surface. For very small delta areas, the area of the tangent plane that sits just above this can approximate the area of that surface, right? If we really think about it, if we just lay down a tangent plane, but really think about a small portion of it, the smaller that we make it, the closer it's going to approximate the area it sits over. So what I'm going to do is I'm going to get some color over here, and you know what? While I'm at it, I think I should just I was just thinking about him today. Dedicate this video to a guy that when he was in my class we called Regular Jason. And he gave me a full box of Hagoromo chalk and Hagoromo colored chalk, which of course will just buy you my loyalty probably for life. But this guy was awesome without any sort of chalk gifts. And so I just want to say that this video is for you, Regular Jason. What are we going to do here? I'm going to draw the tangent plane. It's going to sit tangent right here. And what I'm going to kind of do is going to kind of say, all right, it's going to maybe go about like that and up like this. And, well, maybe that's actually probably not the best trajectory for that edge of the plane. It probably is going to want to go kind of up this way. But it's going to only want to go this far. And so about like that. And then what I'm going to do is I'm going to kind of erase the rest of it so that you're not going to be as distracted. I think. We'll see. This drawing that I made when I made it in class, it didn't go so well, so we'll just see how this goes. All right, yeah, it does not look great, but you can envision it being tangent, right? All right, so what am I going to do next here? All right, so I'm going to label this amount of area inside this kind of restricted plane that does sit tangent to the function at this point. I'm going to call this delta t. And then I'm calling this amount of surface area of this surface that's actually, kind of covered up by the tangent plane since I erased. I'm going to call that delta S. And I'm going to say that for small delta A, right, because delta S is the amount of the surface that sits above delta A. For small delta A, I'm going to say that delta S is approximately equal to delta T. Okay, the area, in an area sense I'm talking about here. And the thing is how am I going to find the area of delta t? That's the big question. Okay, and well, I think what I'm going to say is that we know how to find the area of a parallelogram. We did that in linear algebra. Okay, I don't think we've had need to do it yet in multivariable calculus. What I'll tell you is if you have two known vectors which are spanning the plane, a parallelogram, the area of that parallelogram is equal to the length of the cross product of the two vectors that are spanning the parallelogram. So we'll get to that. I think what I need to do first is I need to kind of talk to you about what does t look like, I don't know, maybe or the front edge of t, this edge, what does this look like if we're just considering x and z? I think I am going to do that, but maybe I'll label these first. I'm going to label this vector here, I'm going to call this one u. going to call this one V. And then I'm going to kind of draw you some side diagrams here. Okay, I probably should use a different color there because that's starting to look a little sloppy. So in order to find out kind of what is going on with you, I'm going to graph Z versus X. So this is going to be the same image as what I was looking at before, except now I'm going to be looking straight at the front of this plane. Now the plane might itself be rising up from the back, but I'm only talking about the front edge because all I care about is like figuring out what's going on with you, you know? So I'm going to go over here, and maybe I'll just kind of draw in the trace of vector u, and maybe I'll draw it in green. And it looks like we're making this happen in the positive area, but you know, I'll just draw it like this. Okay, I've got my u. All right, now what I'm proposing is that, okay, this width here is like a delta x, right? If you think about it, this is, you know, potentially tilted in some way depending on the nature of the curve, right? So that's where the partial derivatives are going to come in. Okay, this might be tilted up a little bit like I've drawn it here, but in this distance, it's the same as this, which is delta x. This is delta y. Okay. So this distance is delta x, and then this amount of distance is going to be equal to delta x multiplied by the partial derivative of z with respect to x. Okay? If you see, the partial derivative of z with respect to x is the slope of this line, and the slope of this line multiplied by this is going to be the change in that. Okay? And if you need to pause and sit with that for a second, that would be completely fine. All right, and now it looks like So I think actually what I'll do, I'll just write down u, and I'll let you maybe try to replicate the same thing for v. But I'll just kind of warn you that since this is the positive y direction and we're coming over here, it might be not as easy to draw like that. So what I'm going to say is that, okay, let's get some coordinates for u, right? All right, so in the x direction, it goes delta x. Okay, that might not be surprising. Okay. In the z direction, it's changing by delta x times dz dx. Now I'm going to write that as fx, just kind of for brevity, but I'll just say that's fx delta x. I'm also going to say that that's going to be 0 because over here, this is maybe not in the xz plane. You know, it might be a little bit behind the xz plane or in front of it or something. But what I'm saying is that it sits in a plane that's parallel to the xz plane, right? Because it's sitting over here. And, well, in a plane that's parallel to the xz plane, y is not changing, right? It's basically, you know, we're sitting at a constant y on there. And then for maybe this edge, which I'm considering to be v, or you know, at least the kind of the downward image of v, I'm looking at a constant x situation, so I've got to think that if u is equal to this, then v is going to be delta y in here, and over here, fy times delta y. X will be 0 because, you know, like x isn't changing on v. Okay? And then I'll know that the area of the tangent plane, or the portion of the tangent plane that I'm interested in, is given by the length of u crossed with v. So I just need to kind of start computing. U crossed with v is going to be the determinant of this matrix. I definitely did not leave myself enough room to really actually compute this thing, but it'll be all right. Delta x 0 and fx delta x. And maybe I'll just give myself a little more room so I can put this. 0 delta y and fy delta y. Okay, we know how to compute a cross product. It's going to be equal to, and I'll just kind of set it up, it's going to be I times 0 minus fx delta x delta y. Okay, minus j times, all right, delta x delta y fy minus 0. Okay, so it's just going to be fy delta x delta y. And then plus k times cover this thing up, and I'll have delta x delta y minus 0. And so I'm going to notice that I've got a delta x delta y in all of these things, and I have a name for delta x times delta y. That's delta a. So I'm going to say that this is equal to, like, how far does my shot go? It's not really going far enough. Let's just set up the camera in a different place today. Okay, roll it back a little. All right, so I'm going to factor out the delta x and the delta y and start calling it a delta a. Okay, so it's going to be negative fx, negative fy, and 1 times delta a. Okay, and so if I'm trying to find the length of this vector, and it's really some other vector multiplied up by a constant, I can find the length of this and then scale it up by delta area. Okay? So the length of u crossed with v is going to be the square root of, I'm going to square each of these things, you know, there and there and there, add them together and take that square root. Okay? So it's going to be equal to the square root of fx squared plus fy squared plus 1 squared delta area. Okay? And this is starting to look like maybe an integrand, right? And so the idea is, right, this is just one very small piece of surface area. And if we wanted the total amount of surface area, we'd add up all of these small pieces. And as delta area goes towards 0, we're going towards surface area equals the double integral over some region of this dA. So the square root of fx squared plus fy squared plus 1 dA. And this is the formula that you would see in, you know, your textbook, right? Oftentimes, these are kind of like the single variable arc length integrals. They're a little hopeless in terms of actually hand anti-differentiating them. But I think I've got an example that's going to work here that I'm going to do for you. I don't think I worked it all the way out, but I think I saw that it was going to be able to be done with a polar substitution. So, you know, we're still somewhat new to our polar substitutions, and I'll just do one of those right now. So I'm going to set up for an example to wrap this video up. All right, so I had to move the formula for surface area because I realized I'm going to need that over there. And so my example is find the area of the paraboloid z equals 5 plus x squared plus y squared that sits above basically a disk in the plane centered on the origin, radius 2. Okay? The set of all x and y such that x squared plus y squared is less than or equal to 4. That's the region I'm interested in. All right, so what I'm going to do is, like always, I'm going to draw the region. I'm going to... I might even draw you the paraboloid. Yeah, that seems a little ambitious. Oh, I've got... No, I'm just going to draw you the region. Okay, so this is region R. Okay, we know what a paraboloid looks like, and I'm just interested in, you know, the amount of area. So what I'm going to do is I'm going to set up the double integral. So it's going to be the double integral over this round region of the square root of, okay, f in this case is f of x and y is 5 plus x squared plus y squared. Fx will be 2x, fy will be 2y. Okay, so 2x squared is going to be 4x squared. 2y squared is going to be 4y squared plus 1 dA. As I have told you before, if you are trying to integrate over a region that is a circle centered at the origin, you got two options, and one of them is really difficult and one of them is much easier. And the easier one is to switch to polar. So I'm going to do that. I'm going to say over here, this is r between 0 and 2, and theta between 0 and 2 pi. And, well, that's basically a rectangle we can integrate over. We'll really like that. So what I need to do is I need to kind of say what's going on here. Okay, remember that my conversion factor is r squared is x squared plus y squared. And dA is r dr d theta. So I can actually make Okay, I'm going to say that by switching to polar, okay, I have the square root of 4r squared, right? R squared is x squared plus y squared. If I have 4x squared plus 4y squared, that's a total of 4r squared. 4r squared plus 1 dA is r dr d theta. So again, here's a situation where this r is actually extremely helpful for me because it's going to allow me to anti-differentiate. It's going to allow me to use substitution. It'll be really nice. So I'm going to say, what is r running from? R is running from 0 to 2. And what is d theta running from? 0 to 2 pi. And then here we have it set up. This is going to be something that we can do pretty easily. All right. And I think that this is the type of thing that you're going to want to do on your own. Okay? So what I'm going to do is I'm going to pause the recording. I'm going to work it out. You should pause the video so that you can do your practice and then, you know, let it play and you'll see the answer and make sure you've done it the right way. All right. So there you have it. I'll be honest, I'm not 100% sure this is right. I didn't like check it or anything. This is an example I made up, so I'd have to go, you know, I don't know, calculate it on the computer or something. And it's after school and it's been a long day. So I think I'm just going to wrap up this video here. If there's anything wrong with this answer, I'll ask that you put some comments down below. Okay, but this is the, you know, this is the formula for surface area. This is where we got it, and this is how we would use it.